is a little rough. So just a broad overview, basically. So our research focuses on crosstalk caused by LEOsat streaks. So recently, Elon Musk and some other billionaires have decided to put up satellite constellations. The problem with this is they're very bright, they're very shiny. So they have a number of effects that are detrimental to survey astronomy and to LSST. So here, what I'm showing is a simulated image. Basically, we have at Davis a beam simulator, which simulates the optics of the LSST camera, and we have a single CCD detector that is the same type as those used in LSST camera. And we have a slit mask that simulates a single streak, like a satellite streak. We put that in focus and we image it. And what you get in these images, what I'm showing is this cross streak. I'm not sure, you probably can't see my, sharing somebody else's screen, so you can't see my mouse. But the middle streak labeled 0 is the main image that's being created. And then where you see the one labeled 1, that's actually a recreated image from Crosstalk, that you go from the same pixel number gets actually, the signal gets coupled to the next amplifier over, and we get a bright streak there too. And then you can actually see a second order and third order crosstalk in this image on the next two amplifier channels. So the three main points I want to make in this are: satellites are bad, they cause bright streaks. For linear crosstalk, so most often this is caused by capacitive coupling, so that is a linear effect, where basically the crosstalk, no matter how bright it is offset in the next channel by a certain amount, something like 10 to the -4 here. And if that's the case, we have 120 amp correlations between on a single CCD. We just have to measure all those, and then we can correct for this. And the third thing I want to talk about is that this is what we're observing is not linear crosstalk in the CCD. We don't fully understand why that's happening, and when that might be a lot harder to correct. So if you want to go to the next image, there's questions in the chat I'll answer later. So this is just an image from our recent paper that talks about LEOsats. So you have on the y-axis the peak pixel count, so the actual brightness that we measure for a satellite, and the satellite's apparent magnitude. And so basically in these different bands that the LSST uses, we can show approximately where we can get correctable crosstalk for linear crosstalk. And it's somewhere around here at like the 6th to 7th magnitude. Elon Musk is actually trying to work with us on that, on making satellites dimmer. Hopefully the other manufacturers will do likewise. So if we want to go to the next slide. So what we do in our lab is we measure with the CCD in, we measure the crosstalk, and the crosstalk ratio is what this is. So it's actually, you take the measured output and you divide that by the injected main amplifier. And so on the y-axis here, we have normalized.
4 minutes are up, so I unfortunately have to cut you off. Sorry about that.
So can I just one sentence?
Yeah.
This is not linear. We don't know why that's happening, and we're not sure how easily it is to correct, but we're working on that.
Okay, thanks, Daniel. Let's go to the next talk. Shu.
Okay. Hello, everyone. My name is Shu, and I'm working in the desk DC2 DRA group. And today my topic is testing the DRA pipeline using fixed source injection. Fixed source injection is a technique used to test the performance of the difference image analysis pipeline. So basically, we can add fixed stars onto galaxies at different magnitude level. And by tracking the fixed stars, we can evaluate the efficiency, purity, and flux recovery of the pipeline. So efficiency is defined as the number of detected fakes over the number of injected fakes. On the right, I plot the efficiency versus fake magnitude. And you can see that as the fake magnitude increase, the efficiency decrease. And when the fake magnitude is really faint, when it is about 24 magnitude, our efficiency starts to approach 0. Okay, next slide, please. Okay, here we check the flux residuals between the detected flux and the injected flux at different fake magnitudes. The flux residual is defined as the detected flux minus injected flux, and then divided by the injected flux. And on the plots, the purple represents the flux residual, and the red represents the 5% threshold. From the plots, we find that at 21 magnitude, most flux residuals are bounded within the 5% threshold. And when the fake sources become faint, the residuals increase. And at 24 magnitude, only a few fake sources are detected, and all residuals are actually about the 5% threshold. Next slide, please. Okay, so there are about 100 flags from the detection catalog, and we find 5 of them are really helpful to remove artifacts. And they are the saturated flag, saturated center flag, dipole fade flag, ash flag, and SDSS shape flag. Since most subtraction artifacts appear in the bright region, so we apply the flags to the DRA source catalog at 18 fake magnitude. And then we calculate the confusion matrix efficiency and purity. We find that our pipeline can achieve a 99.7% efficiency and 87.9% purity, which means the pipeline works quite well. So that's all of my talk. Thanks.
Great. You actually have 50 more seconds left, but let's just move on to the next stuff.
Okay, hello everyone. I assume you can hear me. Everything's gone fine. My name is Tom Wilson, and today I'd like to talk to you about our catalog cross-matching service we're providing through the LSST UK consortium, macauff. I imagine most of you, when doing your science, are going to merge the Rubin Observatory's LSST with some other data set in some other photometric catalog in some way, and quite a few of you probably plan to do nearest neighbor matching to combine your data sets, where you take your LSST source and you ask all the sky separations between it and all the sources in your other catalog, and then you take the source with the smallest on-sky distance. But this simply won't work for LSST, because at the median density in the southern sky, you can expect something like 10 randomly placed objects in each nearest neighbor matching radius, leading to too many false positives and untrustworthy cross matches. Next slide, please. So you should probably turn to more advanced matching methods and consider probabilistic cross-matching methods. But why should you use our Bayesian cross-matching service, I hear you cry? Well, I think there are 2 very important reasons to consider macauff over other cross-matching services available out there. First, we can reject these 10 or so false matches that you'll find around each LSST object at full depth using the photometry of the sources, which not every catalog cross-matching service does, where we can consider the correlation between brightnesses in sources in LSST and in your other catalog on something like a square degree patch of sky, providing the probability of sources being matched not just on position, but also on brightness. The key here is that if you have a 15th magnitude object in LSST, everywhere in the sky those sources exist, there should be a 15th magnitude pan-stars object, say, for example. So the correlation between every single source having its brightness holds as an ensemble. Second, my second point here is I think we are the only cross-matching service that considers other sources of potential separation between objects in catalogs other than the certainty with which the pipeline measured the source's position on the image. This is very important for LSST because it's such a dense data set with a very faint completeness limit, where we uniquely consider the effect that blended objects have on the positions of the brighter object in these catalogs, where the faint object undetected by your pipeline, the LSST stack or whatever you use to reduce your other data, will tug on the center of light of the brighter object, causing a deviation of its position away from true, quote unquote, which will lead to a larger separation between objects than you would otherwise assume, where the key figure here is the black and the red data in that little figure I've put on the right there. Next slide, please. But extending this, because we've generalized the description of the uncertainty in a source's location, we can actually include other effects such as proper motion where sources drift across the sky, which is very important for LSST as well, because LSST will have no known proper motions for most of its sources for most of its lifetime, but also because there'll be up to a 30-year baseline between the sources the positions it measures and things like 2MASS way back in 2000. But we also plan to provide a real-time matching service based on the LASIR broker screen, where you hopefully saw the talks yesterday about that, where our unique modeling of systematics affecting object locations will be very important for the modeling of these sources, where a supernova, which used to be 20th magnitude, suddenly becomes 15th magnitude and suffers different amounts of blended source perturbation because it's suddenly the dominant source in that patch of sky. And finally, because we have to model the effect that these blended objects have on the positions of sources, we can actually provide users with information about the level of photometric contamination that they suffer, which allows for the distinguishing between a star that has a true infrared disk excess, because it's a young star with a disk, or one that is just too bright because there's this second object that's been merged with it that we haven't detected, and therefore we've added the fluxes together. And just very quickly to say, we're providing many catalog to LSST matches, so please do get in touch with me if you are worried that we aren't including your favorite data set in our matches. Thank you.
That's perfect, with 4 seconds remaining. And let's go for the last talk by Sid. Take away.
Hi, my name is Siddharth Patel. I'm a third-year undergrad student at the University of Delaware. For the past 10 weeks, Rubin Rhapsodies has been my summer project. The goal of Rubin Rhapsodies is to prototype a method of sonifying Rubin data and turning data into sound. I did this by using the Plastic Challenge dataset and a couple of Python libraries. The motivation for this project is to see how else we can interpret Rubin data and in a way that can allow people who can't interact with the data visually to do so in an auditory format, but also sonifications could be used complementary to visualizations. This allows for different ways of interactions and allows for more people to work on the data Rubin Observatory provides. The data is for everyone, so everyone should have a way to work with it. On top of all this, sonifications sound pretty cool, so it can be one avenue for public outreach. Next slide. Here is a simulation of how a supernova type 1BC could be observed by LSST straight from the plastic dataset. And it's a very simple sonification and arguably one of the more pleasant you'll hear today. I just mapped time to time and flux to pitch. Note that there are a couple of high-pitched sounds, so you may want to lower your volume. Next slide. Right. It's fine. Next slide. Here's the exact same object as the previous slide. However, this time I've included more data features to the sonification, which is uncertainty to volume and each bandpass to its own instrument. Next slide. Next slide. The last sonification was quite complex and confusing, so I have 2 more sonifications with the exact same feature mapping, played only with one bandpass. Next slide. Next slide. Here, the Y bandpass, if you go back. Yeah, pause it. Here the Y bandpass was played and it was given the tuba as its instrument. This is because tuba has like a lower pitch range. So we mapped it to, lower wavelengths. Next slide. So there isn't a single or standard way to map features to sound properties. Here, for example, we can have an alternate mapping where we map time to time as usual, but instead map flux to volume and bandpass to pitch. But in this example, we lose information on the uncertainty. So let's play the sonification. Next slide. Next slide. Rubin data is very complex and contains a lot of information. It would be very difficult to map it all to sound, but we also have many features of sound available that we haven't explored yet. So it is possible to incorporate more Rubin data into sonifications. Thanks for listening, but Zoom has its problems. But yeah, that's it.
That's great, Doug. Let's applaud all our speakers, please, and let us also open it up for questions. Claire, do you want to read out questions or ask them down?
Yeah, sure. So there's a couple of questions in the chat that have already been answered, but I'll read out the others and feel free to either raise your hand or add some questions in the chat. So there was a question for Shu from Pat. A question of clarification. Are the fake source injections made on single exposures, for example, for real-time DIA?
I'm not sure what the real-time mean here, but in my project, the fake source is added to the calyx exposure. So basically, each calyx exposure is a single image. So does that answer your question?
I think it probably does, yeah. And then there was a question from Eric for Tom, which might already have been answered. What are you assuming for SEDs when matching across catalogs, and is that user configurable in your package?
Yeah, so I guess I'll read out what I said, which is we don't have any models. It's basically a very naive Bayesian classifier in a sense, where we use these correlations between you. If you match LSST to pan stars, every 15th magnitude G LSST source should have a 15th magnitude G pan stars object spatially resolved with it. So we use that assumption, and then essentially the difference, you have 3 other sources around every random 15th magnitude source, but those are all different. Resolve your counterparts and your field stars, as we refer to them, or we need a new term now that we're fitting galaxies with LSST. So this idea of match versus non-match is correlation versus randomly placed. So there's no assumptions. You just need enough data to build a representative in your classifier, basically, which is why we need to do it on something like square degree patches of sky.
Great, thanks. I think that's all the questions we had. Does anyone else want to unmute and ask anything?
I would quite like to ask John to respond to my response to his question. If I can publicly provoke a response.
Yes.
Sorry, which response were you looking for a response to?
The thing about the deblending.
Oh, yes. Okay, right. So your answer made sense in that you're trying to deal with sources that are, I mean, I almost wouldn't call them blends. I would call them.
Sorry, would you mind maybe recapping the original question? So we're on board.
Okay, you go.
You go ahead, Tom.
So the question was, which LSST deblending code are we referring to? Have we looked at Scarlet deblends? To which I attempted to, I think, overcome this difference in language, where when we refer to a blend, we are talking about a source that is at least 3 or 4 magnitudes fainter than the bright source, it is well within the object. You would never resolve it. And in some cases, certainly with WISE, which is our data set, you wouldn't resolve this object even if it was in a completely clean patch of the sky. These things are below the completeness limit of your survey, and they subtly target the resolved, the measured position of these objects, which compares, I think Scala is this idea that if you have two big galaxies and they're resolved objects and they overlap, you want to basically figure out how much of the flux in the bit where my fingers are here is in which object, and we're entirely only dealing with unresolved sources.
Yeah, I would confused sources maybe would be a better
yeah,
to distinguish it from blends that you can actually deblend.
Yeah, I've realized this. Yeah, Scarlet deblends has come up a couple of times, so I do need a new word. Yeah. But this does affect galaxies. In WISE, you still see unresolved point source galaxies perturb the center recorded position of sources in the galactic North Pole. So galaxies don't get away with this. They're just unresolved point source galaxies ruining your day instead of unresolved point source stars ruining your day.
Good. There's also a question for Sid in the chat. Is your output MIDI file that can be played by any sound font of choice? I'm thinking about how different synthesizers might sound with the data. This is a question from Ted.
Yeah, so I haven't explored that yet. I just plugged it into this Python library called Pygame, and it just played back the MIDI file. But I'm assuming you can, because like I think all the information about the instruments and the sound is like hard coded into the MIDI file. So pretty sure it should work out.
One more minute left in this one question from Patel. Yes.
Yeah, go ahead.
Take that and then let's shuffle rules.
Sure. I have a question for Daniel. If you go back to your simulated streak, I think you said it was a pure simulation. I was just wondering, in the upper left-hand corner where the streak is thinner, what does that do to? Is that a real effect?
So simulation is a weird word. This is actually an image of a slit that we're running through some optics. So it's a simulation of what the LSST actual beam is like, but it's a real image. So the small variations, we're machining a 4 micron thick slit. So small variations could be just from that.
Got it. Thanks.
Cool. I see there's a question from Eric, but I think we should switch breakout rooms or shuffle the audience anyway.
Right. I think if you can just post your question on chat, that would be helpful, but we'll have to move on. Let me pause the recording for.
Cool. Hopefully we've got some new audience members. So let's get started again. Welcome to the image processing and statistical methods research Bytes. Before we get started, I just wanted to remind everyone of the code of conduct that we agreed to, which you probably heard about in the previous session you were at. But this includes a respectful and inclusive learning environment, no toleration of discriminatory behavior, and an agreement to report any harassment you witness. And the full code of conduct is available on the PCW website. And secondly, we are recording this session, so just be aware of that. And their recordings will be posted on the session page along with the other slides and session materials. And as in the first go around with these breakout rooms, we'll be taking questions at the end of all 4 speakers. So feel free to put your questions in the Zoom chat or raise your hand at the end. So let's get started with Daniel.
So our research deals with satellite streaks caused by the constellations being put up by Elon Musk and other billionaires. These have a number of effects on survey astronomy and the LSST. One of the main ones that we study at UC Davis, Adam Snyder and I, is crosstalk effects in the camera CCDs. So what this image is showing is the very bright central beam is an imaged slit mask that we simulate the LSST's beam and image onto a single CCD like those used in the camera. And what these other lines are what's called crosstalk effects, where basically between the channel amplifiers, the image is replicated on the respective column. And so the next brightest line is a first order crosstalk in the nearest neighbor channel, whereas label 2 is the next nearest neighbor, and then the next nearest neighbor at 3. So we actually get like 3 orders of crosstalk here. Usually crosstalk is a linear effect that basically for a given brightness, you have a correlation multiplier that you can just calculate how bright the crosstalk effect would be, and then it would be correctable. For a given CCD with us, there would be 120 amp correlations because we have 16 amplifiers, and we could coordinate with whoever has the satellites to just run them over LSST, and then we would be able to categorize that out. The problem that we're finding is that crosstalk is not linear in the LSST CCDs. And so those are the big 3 takeaways I want you to have. So next slide. So what this is showing is on the x-axis, I have the source signal ADU, so the actual readout of a given amplifier. And then what I have on the y-axis is what's called the crosstalk ratio. So it's actually the ratio of the crosstalk signal to the actual source signal. And so and we have this scaled to the high end to be 1. So basically what this is showing is in all of these amplifiers, we're not actually getting linear crosstalk with source signal. We're getting this weird nonlinear. So this is actually, this could be either from the CCD or from the electronics. So what we did was we injected a voltage directly into the video channel electronics past with the CCD unplugged, and we got, and we read that out, and we actually subtracted that from the overall signal. So there's some nonlinearity. It's not happening in the electronics, it's happening on the chip. We don't know exactly what's causing that. So that's my talk, or as much as I can cover in this amount of time.
Thanks, Daniel. Let's move on to the next topic.
Okay. Hello, everyone. My name is Shu. I'm working in the desk DC2 DIA group. And today my topic is testing the DIA pipeline using a fixed source injection. Fixed injection is a technique used to test the performance of the difference image analysis pipeline. Basically, we add fixed stars onto galaxies at different magnitude levels. And by tracking the fixed stars, we can evaluate the efficiency, purity, and flux recovery of the pipeline. The efficiency is defined as the number of detected fix over the number of injected fix. On the right, I plot the efficiency versus fig mag, and you can see that as the fig magnitude increase, the efficiency decrease, and at the fin end, the efficiency starts to approach 0. Next slide, please. Okay, so here we check the flux residuals between the detected flux and the injected flux at different fig magnitudes. The flux residual is defined as the detected flux minus injected flux, and then divided by the injected flux. On the plots, the purple represents the flux residual, and the red color represents the 5% threshold. From the plots, we find that at 21 magnitude, most flux residuals are bounded within the 5% threshold. And when the fake sources become faint, the residuals increase. And at 24 magnitude, only a few sources are actually detected, and all of the residuals are above the 5% threshold. Next slide, please. Okay. There are about 100 flags from the detection catalog, and we find 5 of them are really helpful to remove the artifacts. And they are the saturated flag, saturated center flag, dipole fit flag, edge flag, and SDSS shape flag. And since most of the subtraction artifacts appear in the bright region, so we apply the flags to the DRA source catalog with injection at 18 fake magnitude. And then we calculate the confusion matrix, the efficiency and purity. We find that our pipeline can achieve a 99.7% efficiency and a 87.9% purity, which means the pipeline works quite well. That's all my talk. Thanks.
Thanks a lot, Shu. Let's go for the next talk, Tom.
Okay. Hello, everybody. My name is Tom Wilson, and today I'd like to talk to you about our catalog cross-matching service, which we're providing through the LSST UK consortium, macauff. Now, I imagine quite a lot of, most of you are planning to use some other data in conjunction with Rubin Observatory's LSST to do your science, whatever it might be. And a fair few of you have probably planned to use a nearest neighbor cross-match to merge these data sets, taking your LSST source, asking the sky separator between it and all the other sources in your other catalog, and then finding the one with the smallest on-sky distance. But this just won't work for LSST, because at median densities in the southern sky, you can expect something like 10 randomly placed objects in each nearest neighbor radius, which will lead to too many false positives and untrustworthy cross-matches. Next slide, please. So you should turn to more advanced matching methods and consider a probabilistic cross-matching method. But why should you use our Bayesian cross-matching service, I hear you ask? And on this slide, I show you what I think are the 2 very important reasons to consider macauff over other cross-matching services that are available. And the first, we can reject these 10 or so false matches that you will see around every LSST object in your full depth cross-match by using the photometry of these photometric catalogs, which isn't actually done by every cross-matching service. Where if we consider the correlations between the magnitudes of sources in LSST and sources in our other catalog, in something like a square degree patch of sky, we can provide the probability of sources being matched on not just position, but also on brightness. The idea being that if you wanted to match LSST to, say, pan stars and you took the G band, every 15th magnitude LSST source should have somewhere on top of it in the sky a 15th magnitude pan stars object, because they're using roughly the same filter. And second, on the right-hand side here, I think we're the only cross-matching service that considers other sources of potential separation between objects in these catalogs, other than the certainty with which your pipeline measured the position of the source on the image, which is very important for LSST, being a dense data set with very faint completeness limit, 27th magnitude. And we uniquely consider the effect that unresolved objects have on the positions of brighter objects in these photometric catalogs, where the faint object, which would completely be undetected by your pipeline, tugs on the center of light of the brighter object, which causes a deviation of its position away from true, which leads to larger separations between objects than you would otherwise assume, which you can see in the figure on the far right there. Next slide, please. But because we've generalized the description of the uncertainty of a source's location, we can actually extend this method to include the effects of proper motions where sources drift across the sky with time, which is going to be very important for LSST because it will have no proper motions for most of its sources for quite a few years of the survey. And at the faint end, you might not trust the proper motions, so you'll still need the, when it doesn't give good proper motions, you'll still need known proper motion modeling. But also because we will have a 30-year baseline between the sources in LSST, the positions they record, and something like 2MATS, which recorded its positions in the heady days of the year 2000. We also plan to provide a real-time matching service based on the LASER broker stream, which hopefully you heard about yesterday at the session. where our unique modeling of the systematics that affect object locations will be important for modeling things like supernovae, where a 20th magnitude source suddenly becomes 15th magnitude, and it now suffers different amounts of unresolved source perturbation because it's now the dominant source in its little patch of sky. And finally, because we modeled the effects of unresolved objects on the positions of sources, we can actually provide users with information as to the level of photometric contamination they suffer, allowing for the distinguishing between, say, a star which has an actual disk excess because it has dust around it and it's a young star, or it's just got a contaminant star buried within its PSF and you didn't resolve it. And just finally to say, we plan to provide many LSST to catalog matches, so please do get in touch if you're worried we're not including your dataset in our matching service. Thank you.
Thanks, Tom. Let's move for the last talk of this session by Sid.
Hi, my name is Siddharth Patel. I'm a third-year undergrad student at the University of Delaware. For the past 10 weeks, Rubin Rhapsodies has been my summer project. The goal of Rubin Rhapsodies is to prototype a method of sonifying Rubin data, turning data into sound. I did this by using the Plastic Challenge dataset and a couple of Python libraries. The motivation for this project is to see how else we can interpret Rubin data and in a way that can allow people who can't interact with the data visually to do so in an auditory format. But also sonifications could be used complementary to visualizations. This allows for different ways of interaction and allows for more people to work on the data Rubin Observatory provides. The data is for everyone, so everyone should have a way to work with it. And on top of all of this, sonifications sound pretty cool, so it can be one avenue for public outreach. Next slide. Here's a simulation of how a supernova type 1bc could be observed by LSST straight from the plastic dataset. And it's a very simple sonification. I just map time to time and flux to pitch. Note that Zoom is funny, so you probably won't hear it, but that's fine. Next slide. Next slide. Here's the exact same object as the previous slide. However, this time I've included more data features to the sonification, which is uncertainty to volume, and each bandpass has its own instrument. Next slide. Next slide. The last sonification was quite complex and confusing, so I have two more sonifications with the exact same feature mapping, however, played with only one bandpass. Next slide. Next slide. So here, the Y bandpass was played and it was given the tuba as its instrument. This is because the tuba has a lower pitch range, so we decided to map it to lower wavelengths. Next slide. So there isn't a single or standard way to map features to sound properties. Here, for example, we can have an alternate mapping where we map time to time as usual, but instead map flux to volume and bandpass to pitch. But in this example, we lose information on the uncertainty. Let's play this sonification. Next slide. Next slide. So Rubin data is very complex and contains a lot of information. And it would be very difficult to map it all to sound, but we also have many features of sound available that we haven't explored yet. So it is possible to incorporate more Rubin data into sonifications. Thank you for listening.
Great. Let's thank all the speakers for their great talks. And let's open up for the Q&A session.
Yeah, we have a couple of questions in the chat, so I'll start with those, but feel free to add some more as we go along. So Bob had a question for Sid. Do we have a link where we can listen to the Rhapsodies again?
Yeah, are these slides available to be shared? Because that would be the easiest option. Yep, there it is. So you can go through the slides and listen to them.
Sorry, I don't know if you didn't just hear the pitch or the volume sound at all. Apologies if that was the case.
No, it's
You can
fine.
hear. Yeah, so there's the link in the chat to anyone who wants to listen to those again. And there's a question from Eric for Daniel. I'm just curious about the difference between a slit and a satellite. So the slit lights up all the pixels along the path simultaneously, while a real satellite does not. So how does this affect our expectation of what we're seeing?
That's a good question. We actually did originally try and simulate the satellite using a moving source. And in the actual bot, I believe they tried running a source across. As far as we're aware, this shouldn't make a large difference because in a CCD, you're still just filling up the same energy wells. And the time ordering of that shouldn't really matter for a given exposure. But then again, we're studying something we don't really understand right now. So it's a good question.
Great, thanks. And there's a question from Will for Tom. He says, great talk. Does inclusion of unknown proper motion greatly increase the computation time? And is that likely to matter in practice?
No, so the trick is you have to reverse engineer a galactic model for proper motion because you assume galaxies don't move on any resolution or anything that matters. The galaxies are fixed. It's really resolving galactic sources, Milky Way objects that matter. You have to run forward model for a given sight line in the galaxy, in galactic latitude, longitude, and distance in some fashion, you get a galactic motion model. You have to forward model those, so those can be pre-generated. So they take some time, but you run them the once. Basically, if you're happy with the model, you then get, as I showed if you could go down 2 slides, you see the distribution of these proper motions times by delta t. You then need to Fourier transform those, but no, after that, it's a multiplication in Fourier space, which we have to do anyway because of the perturbation due to these blended objects. It's convolutions, which are multiplications in Fourier space. So it adds 1 extra Fourier space multiplication, which you have to inverse Fourier transform anyway. So it shouldn't greatly increase the computation time once you've pre-generated your model, basically.
Great, thanks. And then another question for you, Tom, from Holger about, I think you answered it in the chat, but I'll say it anyway. Have you thought about including this matching algorithm as part of the virtual observatory?
Yes, so I'll say my answer in the chat. Yes, that is definitely something we want to do. This is a new world for me, virtual observatories, TAP services, all of this stuff we're looking into. The TAP service is the primary thing that we, as part of the LSST UK, have a remit. That's something we have to commit to, but we're absolutely looking into these other things. And then I'll just tack on my response to the follow-up question of, could other brokers run this algorithm? Absolutely. I mentioned Laser specifically because, again, that's the LSST UK streaming service, so that's the one that we're able to talk to. But I absolutely would love to talk to other people about whether we can connect this to other things if this is something you need, if you're worried about these transient objects and would like to resolve these contaminant blended unresolved objects in your matching service, please do get in touch.
Great, thanks. I actually had a question for Shu while I wait for other questions to come in the chat. You quoted the efficiency and the purity of your model in the end. So I guess sort of 2-part, can you remind us what purity is? And I noticed that number is lower than the efficiency. So is that a decision you made to optimize for higher efficiency?
Okay, so here the purity is the number of true fixes over the number of detected fixes. So basically, our detection has true fixes. It also has artifacts, and only a part of the artifacts get the flags. So we can see they are actually the artifacts, but there are some artifacts which has no flag. So we also treat them as fake.
Cool. And so did you, because I know in some machine learning models, you can sort of decide which ones you like, where to put some cutoffs to sort of tweak whether you're going to concentrate on the number of true fakes versus false positives. Is that something you had to do, or was this just what came out?
So here for this project, we just want to recommend a few flags that are useful to select artifacts. And actually the DIA group has other projects to apply more complicated learning algorithms to remove artifacts.
Cool, thanks. I don't see any other questions in the chat, and there are no raised hands.
Probably 30 minutes maybe, in case people are still coming up with questions.
I guess, Daniel, you said that you don't really know what the nonlinearity is coming from. Do you have any like guesses or any ideas?
Well, we know that it's an on-chip effect, and we know that we have some rabbits to chase down holes, but there's not a definitive source that we know of that is causing this yet.
It's also particularly interesting that it goes up high and then comes down to 1 by a normalization. But yeah, I'm also quite surprised it's not monotonic.
Right. If it was just going up, it would be pretty easily explained by just an offset or something. We haven't been able to definitively, we haven't been able to show that there's an offset. We're pretty sure it's not an offset issue. Mm-hmm. All signs point to an on-chip effect.
Cool. Do we have any final questions for the speakers? Not, let's thank all the speakers once again. And should we call it an end, Claire Ellis? Yeah, okay.
Yeah, I think that sounds good. Thanks everyone for listening and asking some questions.
Yep. And
thanks to the speakers again.
Yes. Have a good rest of the PCW then. See you in other sessions.
Thanks everyone. Thanks for a good moderation.